Please highlight that section, that sentence that says this is the most common test on the AP test. Okay, so of all the tests you guys have, this is going to be the most important one, the one that will show up on the free response as 5 to 6 points for this one part test. Okay, so just do your best today, you guys, to try to process this information, because again, it is very abstract and conceptual here. So the ratio tests, we're going to start off with something just more grinding out another test, and then I'll talk to you guys about what happens when we have an alternating series. Okay, so again, we're presented with a test with a restriction that the terms have to be positive. And according to this test, and this is the way that I think of it, you guys, if you let n go to infinity of a geometric series, right, and you think about putting the n+1 term over the n term, well, the result of that is going to give you guys what normally is like, okay, so if you take the second term, put it over the first term of a geometric series, you get R, you get the common ratio. It's the second over the first, or the next term over the previous term, it results in R. Although this isn't exactly the same, it has the same results as the geometric series. And since we already memorized the geometric series test, why not use that to help you guys remember this? So if you take the n+1 term, put it over the n term, get a value. If that value is less than 1, similar to like your common ratio, then the series converges. If it's greater than 1, think of the next term over as you're multiplying it by a number bigger than 1. So those resulting terms are going to get bigger and bigger. Therefore, your series is going to diverge. The only tricky part about the ratio test that you guys will have to remember is that if it equals 1, the test fails. So if you guys can put a star by this and say, move on to another test. Okay, so C does not, C, if you get C as your answer, then move on to another test means that try something else, integral test, LCT, P series, whatever it might be, it doesn't work with the ratio test. Okay, so example 10, how do I know to use the ratio test? The ratio test works for a lot of the series, that's why it's the most common one on the AP test. So for example, this one, can you guys type into the chat actually? What's one test that you guys can use on this one that you've already learned? Anyone have any ideas? I don't know if you guys are there yet, if you can just look at it and recognize. Yep. Okay, so I had someone guess LCT to LCT to, where is the n? And I was talking to someone about this. If the n is in the exponent, it's a geometric series. If the n is in the the base of a expressions like n squared or n to the third, that's a P series. So this is a geometric series. If you did LCT to a geometric series, the geometric series 2/3 to the nth power converges, therefore this series converges. Now let's say you guys didn't recognize that. So we're gonna apply the ratio test. Anytime you guys have lots of things going on with the powers, if it looks confusing, like there's a lot of stuff going on, it's probably gonna be the ratio test. You're gonna like the ratio test, it's very simple to apply. So what you're gonna do is do the limit as n goes to infinity. I'll explain in the next page, but for now, if you guys can insert absolute values around the top, let me circle it, around the n+1 term over the n term, can you guys go ahead and stick absolute values around that? Okay, sometimes those absolute values are going to be significant, other times it doesn't really matter. So for now, when it says it has to be positive terms, these terms are already positive. What does it mean by positive? If I plug 0 into here, then 1 into here, the successive terms that I get in this series are all positive terms. The only times that you're going to get that they're negative terms is potentially when they're alternating. But this series we can see is not alternating. There's nothing negative about it. So sticking the absolute value bars there is not crucial because they're all positive anyway. However, just as good practice, I'm just going to have you guys do it just in case, and it doesn't hurt eventually to acknowledge that it could be negative, and then you don't have to worry about it. If we just make it a habit of taking the absolute value of everything, then we're good to go. So the n+1 term simply means you're going to take the nth term, which is your general term, and increment all your n's by 1. Okay, technically have an absolute value bar around it. Okay, if you guys can watch but not write out, because I'm going to put this as a step, but then eventually take away this step. So don't write out the next part. Technically, you guys, what I just did, this is the n+1 term. I'm going to put it over the nth term, but you guys don't do that. Again, just watch me do this because it just feels like an unnecessary step for me. 2 to the n over 3n plus 1. So that's this represents the n+1 term over the nth term. Giant absolute value bar is going down the entire thing. But when we are doing the ratio test every single time, you guys are going to keep the top, change the division to multiplication, and then multiply by the reciprocal. So I skipped this step of putting it as a ratio, and then I just go straight into multiplication, which is what the free response does as well. So let me erase this. Okay, so your first step is going to be n+1 term. So this is your n+1 term. And then you're going to times by the reciprocal of your nth term. So take your nth term, flip, and then you get 3 to the n on top plus 1 all over 2 to the n. Okay, on this first problem, I'm going to regroup it. You guys don't have to rewrite it after this, but for this first problem, I'm going to do this for you guys so that you see what I mean. You're going to group things that are similar to each other. Similar as in they have the same base, or they are what you would compare the nth term, the n+1 term. They're similar in that sense. So in this case, the 2 to the n+1 has the same base as the 2 to the n. So remember, multiplication is commutative. So I'm just moving things around, shuffling it around so it's easier for me to analyze the limit. Okay, so rewrite it, regroup things. So when we take a look at 2 to the n+1 over 2 to the n, let's look at that part first. Technically, there's absolute value bars around here. We can drop it at this point if we recognize that all terms are positive anyways. So if I asked you guys in Algebra 1 to simplify this expression, and that expression has a common base, what would you guys do with the exponents? If you had to combine those two things, you would subtract, and you would subtract towards the top because the top is bigger than the bottom, right? So you have n+1 minus n. So what we're going to do is, if you have a different color, you guys can do it in a different color and basically cancel it out so that you just have 2 to the first power on top. Okay, reduce that, simplify that out. And then same thing on this side. This is overall a limit that where n goes to infinity. So as n goes to infinity, these +1s are negligible. You can drop it out of consideration and look at overall what you guys would have left just with this piece here. So again, we have something that is exponential. So what we'll do is simplify the 3 to the n and the 3 to the n+1 to get that, and again, technically this kind of cancels each other out. You have n+1 is bigger than n, subtract towards the bottom, and you have a 3 left over at the bottom. Okay, so overall, your answer is 2/3. We take our constant value, go back to the analysis above, and if we think about this as a common ratio, and that's exactly what the common ratio is for the geometric series that I would have compared it to, 2/3 to the n. So this happens to be smaller than 1, less than 1, so therefore your conclusion is that it converges by ratio test. I didn't have to figure out what I was going to compare it to. I didn't even have to recognize it was a geometric series. I did the ratio test. It's a little bit longer. If you guys, once you guys get comfortable with it, I would say that you'd probably picture this problem more as a LCT to a geometric series rather than applying the ratio test. But it's always nice to have that as a backup as well. So let's move on to 11. And for some of these, I'm going to jump around. So here is a classic problem that you would know to apply ratio tests for. You have a complicated expression. It's clearly not just geometric because you have this part that's to the nth power, but then this right here is not in the exponent. So when you have things that are combined like that, where you have like n is the base and then n is the exponent, that's automatically ratio test. So the other thing that I'd like you guys to compare this problem to, can you guys type into the chat, what's the difference? There's a huge glaring difference between question 10 and question 11 within the series itself. And maybe let me zoom out and see if you guys can recognize what's the huge difference between the series that you guys have above and then the series below there. Okay, good, Brandon, there's an X now. Okay, so now you start to look at these questions as this is an equation that they're asking you guys to solve for X for. So when they ask for things like radius of convergence and interval of convergence, you're solving for X, okay? What is the values of X that make this series converge? So here, they asked you guys specifically for something called a radius of convergence, which we touched upon briefly on the previous video. If you guys have an interval, you picture the interval to be your diameter. The center is the center that we've been discussing like in the Taylor series, and the radius would be exactly half the interval. So on a radius of convergence question, those questions are going to be like your short questions because all you have to do is figure out what the interval is, cut it in half. Okay, you do have a question on the quiz and it's geometric series. I'm going to go over a question like this at the very end. But if you have an interval, let's say -1 to 1 for a geometric series, we know that that's the interval of convergence. The radius of convergence would just be 1 for a typical regular geometric series. Okay, so if X has to be between -1 and 1, that's your diameter, the radius would be 1. So here, let's go ahead and answer this question. I noticed that it's got a lot of things going on with n, so I'm going to go ahead and move to ratio test. And if I can have you guys start to write out your limit as n goes to infinity, and let me talk about where I insert these absolute values. On the problem before that, I just blanket put the absolute values outside the n+1 and n term. Now that I know, as I plug 0 in to infinity, the n's are never going to be negative. If I start my increment off at 0, it's never going to be negative. So therefore, what I'm going to do is just the only thing that could possibly be negative is this x. So the absolute value bar, instead of putting it and it just being so ugly on your expression, just put it around the x part. So I'm going to keep so remember it's n+1 term, so increment everything that has n in it by +1. Absolute value bars go around the x. And as you're doing this, kind of pay attention to the fact that there are 3 things that had n in it. n+1, the powers for x, and the powers for 10. And then we're going to multiply, so technically over the n term, but we multiply by the reciprocal of this. So then that's going to get me 10 to the nth. So again, I'm just flipping the nth term over n times absolute value of x over n. Okay, so since this is again the second problem, and there's 3 things going on, I am going to regroup things for you so that you guys can see it. So regroup things that are similar. One of the things that are similar is the n+1 and the n. Okay, so we're going to regroup that. We're going to regroup the expressions with a base of 10 in it. Then we're going to regroup things with x's as the base. Okay, it's very confusing for students when they look at this, that there is a difference, but I want you guys to take note of this at this moment in time. If you notice these 2 expressions, the n's are in the exponents. So think geometric series. The n's here are not in the exponent. Okay, so the limit is different when we apply it for these 3 things. So these 2 things we're going to simplify the same way that we did on the above problem. We're going to reduce the exponents. So this one, there's more 10s on the bottom, so there's 10 to the first on the bottom left. These guys, the base is x, so exponential exponents simplify with x to the first on top. Okay, so you go through, simplify your exponential expressions, and then now go back to this expression of n+1 over n. If this stuff didn't exist and you guys were just taking the limit as n goes to infinity, can you type into the chat, what do you guys get when n goes to infinity of n+1 over n? Okay, ratio of the leading coefficients, right? They both have the first power. So think of horizontal asymptotes, they grow at the same rate. So you can essentially cross this off or just say that this is going to go to 1. Okay, these are all products. So you have 1 times absolute value of x over 10. So let's write what we have left over. This is all we have left over. Does that make sense to everyone before I move on? How I collected just that, basically simplified those 3 things down to absolute value of x over 10. That's all that's left. Okay, so the difference between this problem and the previous problem was the previous problem, when there was no x to begin with, I just got a constant value and I made a determination that one series did converge. This one, I have an x in it. So think of this as like an algebra problem now. Okay, if it's an algebra problem, this is the result of my ratio test. For what values of x will this series converge? I'm going to say by the ratio test that the result of this must be less than 1. So we're going to solve this as an algebra problem now. So if I know it has to be less than 1, we're going to solve for the interval from there. Absolute value of x must be less than 10. To rewrite this so that it makes sense, you're going to say x must be between 10 and negative 10. So there is my interval. Now the question is, if that's my interval, can you guys type into the chat, what is my radius? If that is my interval, which I'm going to picture interval as diameter, and then radius as half the length of the diameter. Okay, good. The answer is, and the radius, think of the radius of a circle. You guys wouldn't provide an interval for it. You would just say the length of it. So the radius is equal to 10. Okay, so usually when the numbers are not symmetric across the origin, you guys can do like 10 minus a negative 10 divided by 2 and get 10. So basically find half the length of this interval. Okay, so picture the interval as your diameter, the length of it, and then the radius is half of that. The center of this interval is 0. There was a question, how do I know that, how did I establish this inequality to begin with? Go back to the ratio test. What was the condition for it to converge? We want to find values such that, x values such that the series converges, so we establish it as less than 1. So what does this all mean? This means that if you guys were to select any values between negative 10 and 10, say negative 6, negative 5, negative 1, plug those values into here, the resulting series is going to be convergent. So for example, if you take 8, you plug 8 into x, apply the ratio test on the resulting series, it will converge. If you plug in 11 into x here, it's going to result in a series that's not convergent, it's divergent. So it gives you guys a range for possible values of x. It's like solving for x. Okay, these questions are fairly easy in the sense that you don't have to worry about something called endpoints. So we're going to talk about that next. So we're going to skip over these 2 questions for now, 3 questions. Come back to one of them before we end. And can you guys go to the next page, page 32? And before I move on to discussing this very, very conceptual and confusing topic to you guys, can you copy down on the bottom of page 32, can you copy down these 4 very famous series? These are specific series that I'm going to reference. And then I'll talk about it in just 2 minutes. So give you guys a break. Easy in the scope of everything, Kaylee. Eventually, when we come back around to it, you'll be like, oh, okay, those are the easy questions. And then to answer your question, negative 11 would also give you something that is divergent. So basically anything outside that interval would be divergent. All right, you guys. So the idea of absolute and conditional convergence. All right, so I'm going to be completely honest with you guys. When students ask me like the Taylor series, I see the applications of it. When you get to this level of obscurity, it's like, okay, what's the point of absolute versus conditional convergence? And I can give you guys the best possible answer, but I don't know the direct application of it beyond the fact that what I'm going to explain to you guys next. So it's not like it's something that I know for sure you can use it in this particular setting. So the difference between absolute and negative. So just keep in mind, every single test that we've done so far has been that there was the condition that it had to be positive terms. The limit comparison test, integral test, p-series test, all of those, it said, okay, make sure that your terms are positive. Make sure your terms are positive. So the question becomes, what happens if your terms aren't positive? Okay, so here is a classic case that you guys see below there. You have an alternating series, one in which the terms, some of the terms are negative. And so when I say, what do you mean by negative terms? Like the actual value of it is negative. So negative 1/4 here, negative 1/16 here. So what do we do? If it's not, if we can't apply those tests, if they're negative, what do we do? So now comes into discussion something called absolute versus conditional convergence. So absolute convergence, first I'll tell you guys how do you test for it, then I'll explain what it means. Okay, absolute convergence, to test for absolute convergence, you simply take the absolute value of your series. So if there were negative terms before, now that you take in the absolute value of it, that negative aspect of it disappears, and it becomes something that you guys can then analyze via all the other tests that required it to be positive anyway. So it's kind of like a workaround, right? If you take the absolute value of it, you no longer have negative terms anyway. So take the absolute value, test the resulting series, and make a conclusion. So let's say you guys took the absolute value. You get a series, like for example, the above series. If I took the absolute value of that, I get a series that eventually I'm going to conclude is convergent. I'm going to do that problem with you guys. Then we would say it's absolutely convergent. But the tricky part is, and I have a meme for it, is when you guys take the absolute value of it and it results in a series that's not convergent, it still could be possibly what we call conditionally convergent. Okay, so there's three options now: absolute convergence, conditional convergence, and then just plain divergence. Okay, so absolute, conditional, and then divergent. So if you, I'm going to skip down below here because I want to give you guys the reasoning behind it. Then we're going to come back to example 15. Okay, so if you took the absolute value of it, and I wrote these notes out, it's like, what happens if the absolute value diverges? Then what you do is you have to apply something that would test for sure whether it's truly divergent. So think absolute convergence as a superpower series. No matter how you rearrange those terms, it's still going to result in a series that's convergent. So when you go out to infinity, like really strange things happen. So like take a look at number 1. Okay, this geometric series is one that we've determined is convergent. If I took the absolute value of the general term, it's still going to result in a series that's convergent. So what does that mean conceptually? If I took 1/2 and moved it to the end, like to the 100th term, and moved the 100th term to be in place of 1/2, the series is still going to be convergent. Okay, so this is an example of absolute convergence. So this is 1/2. No matter how you guys rearrange it, it's still going to be convergent. This is a super powered convergent series. And also, you guys want to think of it as like, you know, as you multiply by 1/2, which is the common ratio, these successive terms are getting small enough, fast enough, such that the sequence of partial sums will actually converge to a specific value. So I'll say that again. These terms, as you guys move from one to the next, they're getting small enough, fast enough, such that the sequence of partial sums will converge to an actual finite value. Now, the most famous series that barely diverges is what we call the harmonic series. That's the most famous P series. So if you take a look at this series, it's identical to the top series in the first two terms. Okay, but what happens with the harmonic series is it barely diverges, because look at the third term after that, 1/3 versus 1/4. The 1/4 is smaller than the 1/3. So on the top function for number 1, it's getting small enough fast enough, but for 2, it didn't get small enough fast enough. So this barely diverges. Okay, so this is the most famous p-series that barely diverges. And so when you guys are memorizing those conditions, remember for the p-series, if it's bigger than 1, it converges. The border value was 1. The border value of 1 results in the harmonic series. Okay, then now we introduce what happens when you have negative terms. Okay, so this is the same exact series as the harmonic series, except for its alternating terms. So this is the most famous conditionally convergent. So I'll switch colors here. This is conditionally convergent. So what does conditionally convergent mean? So this is a weak convergence. If I have a series that is conditionally convergent, it's conditional upon the order in which the terms appear. So if I were to move the negative 1/2, say to the end of the series, whatever end means, because let's say you just move the series or rearrange the terms, you could get it to diverge. It could potentially diverge if that's the case. If you rearrange it, a conditionally convergent series, in theory, you can rearrange it so that it diverges. You can rearrange it so it converges. That aspect of it, it's a series that is weak in convergence. Okay, so we're going to figure out how do we test for conditional convergence in just a minute, but notice that the terms are alternating. And one argument for this is also the negation of some of the terms. It's like it's canceling out because it's not going or the value of it is not getting smaller fast enough, it does benefit from the fact that some of the terms are negative. So that's going to cancel out some of the positive aspect of the terms getting as we increase and move on from one term to the next. So the negative part of it, it is benefiting and potentially converging because of that. And then the last thing we have is the alternating geometric series. So with that one, that has the double benefit of the terms getting small enough, fast enough, you're timesing by negative 1/2, but you also have that negative aspect to it. So this is like super, super convergent. So that's the theory behind it. You're not going to be expected to regurgitate any of that information that I just gave to you. I came up with that page because I know over time kids are like, well, what is the difference between it? Okay, so that's the conceptual. Now what you're expected to do is tell the reader, you know something is conditional or you know it's not. So going back to this question, how would you attack this question? There's a couple of homework assignment questions that you've already had on homework 14, where they give you guys the expanded series and you just have to come up with the general term first and then determine convergence from there. So for this one, let's say we started off n equals 1 to infinity, and we just played around with this. So we noticed that what's changing in all of the terms is the base. So we're going to call this over n being the exponent, that's changing. And then n starts with 1. So I'm going to start it with n, and all the exponents are squared. It also happens to be alternating. So I'm going to say negative 1 to the n first. Let's say that's my initial guess. Okay, when you guys come up with the general term, plug it back in. If I plug 1 back into the exponent, I'm going to get a negative value, but I need this to be positive. So you can make a couple adjustments to that. You can either add 1 or you can subtract 1, and either one is fine. So when I do that, if I add 1, now if I plug 1 into here, I get squared, and then that results in a positive term. So that's going to be my general term for that series. Now notice that if I gave you guys this problem last night, which there was a question like that on the homework assignment, you would have said, I can't do this because the terms are not all positive. So then after today, what you guys are going to do is take the absolute value of the whole thing. Okay, and this is the process of testing for absolute convergence. So if I take the absolute value of everything, I get just 1 over n squared left. Okay, you guys in the chat, does this converge or does it diverge? Okay, good. You don't have to write this sentence out normally. I'm just writing it out just so that it's in your notes. So when you guys go back to it, you can, it'll sort of make sense to you, or hopefully make sense to you guys. Since the absolute value of your series converges, you're done, you guys. So once it converges, you can conclude that it absolutely converges. Okay, the original series absolutely converges. So it's a strong convergence. Okay, so that's going to be a blip in the next problem. The next problem is going to be the huge problem as we continue and move on further. So here is, I was trying to think of a flow chart for you guys when I came up with these notes. And this is what made sense to me when I am doing a problem. What we just did was we tested for absolute convergence. Okay, I took the absolute value of the general term, and then I analyzed it based off on all the other tests that I know, and I concluded it converges absolutely. Then you're done. Okay, the next few examples, what's going to happen is when you take the absolute value of it, you're going to find that it's divergent. If it's divergent, you're not done. You have to then move on to test something called the alternating series test to determine if it converges conditionally or if it truly does diverge. So let's move on to an example and see what that means. Okay, the alternating series test, that's our last test for today. Okay, for this test, notice that the terms are alternating on this series. Okay, what we want to know is that if I were to take the absolute value of it, that the absolute value of its terms actually are the terms getting smaller. So this test is really easy. You just write out what you want it to be, like the conditions that you want it to be, and then you double check, well, are those conditions true? So there's going to be a statement that you write for one, that the terms are getting smaller. And then the second statement is going to say that if you take the limit as n goes to infinity of your nth term, it actually goes to 0. And that's going to guarantee that your terms actually get small enough and your last term is going to be indeed 0 if you go out to infinity. And that's going to guarantee that it does converge. Okay, so let's say you initially do this problem the same way we did the previous problem. We test for absolute convergence. So again, I'm writing it out a little bit more detailed than you will eventually be expected to do, but I want this in your notes. Okay, so you guys test for absolute convergence first, which is simply taking the absolute value. Okay, when you take the absolute value of your series, what's going to happen is that the alternating part of it, the -1 to the n+1, it drops. So it simplifies your expression so that when you guys test for absolute convergence, you're really just testing for 1 over cube root of n. Okay, you guys in the chat, does that converge or does that diverge? 1 over cube root of n. We see that that can be written as 1 to the 1 over n to the 1/3 power. That's a p series. The p value is less than 1, so it diverges. So in my mind, this is not absolutely convergent. But because you guys began with an alternating series, we're going to move on to the alternating series test to see if it's possibly conditionally convergent. So AST checks to see if it's possibly conditionally convergent. So test AST. And the test for AST is 2 simple statements. Okay, your first statement is that you're going to say, and this is always the absolute value that you're doing. So I dropped the alternating piece to it. And then I want to double check, is the next term less than the previous term? So n+1 term, is it less than the nth term? So what you do is you just write that statement, almost like, I want this to be true, let's just write it, and then we think about it. Okay, so write what has to be true, which is that the n+1 term has to be smaller than the nth term. Then double check that statement, is that true? If you add 1 to the denominator, it's going to make your fraction smaller. So therefore, this statement is true. Okay, so that's what you do every single time. Write what you want to be true. Double check, is it really true? The second thing is the same thing. You're going to make sure that as you guys go out to infinity, that your nth term also goes to 0. So limit as n goes to infinity of 1 over cube root of n must be equal to 0. So double check, write it out first, make sure it's true. And if it is, if both of those statements are true, then it passes the AST test. So is that statement true? As you guys go out to infinity, does that limit equal 0? It does, right? So when you've check marked both, if you don't check mark one, then it fails. If you check mark both, then it passes AST. So all of that, you guys, is to lead you guys to conclude that this is conditionally convergent. So if it fails absolute convergence but passes AST, it's conditionally convergent. Okay, that's what's expected of you guys to be able to do is to test that convergence. Guess what, you guys? That's, you know, like when you reduce a fraction, that's like a step in a problem. This problem is a step within a larger problem. You guys ready for the big problems? So these are like the 5 to 6 point questions on your AP test is the next example. Okay, so, and again, we're gonna get a ton of practice on this. This is gonna be kind of the culminating problem of the ratio test is the test that is to come. Or actually, you know what, we're gonna do one more practice problem with this before we move on to the bigger problems. All right, you guys, example 17, kind of a smaller problem here. Can you guys go ahead and do our run through test for absolute convergence for me? Go ahead and test for absolute convergence. Feel free to look up if you guys have to. As you guys do this problem, note that this is the alternating harmonic series. This is the famous one, that if we didn't have that negative there, it does diverge. But because there's that negative part, we move on to AST. So if I take the absolute value of it, I'm going to get a P series. The P value is 1, the exponent is 1. So it is not absolutely convergent. So go ahead and try AST on that to see if it's potentially conditionally convergent. We want to make sure that the terms are successively getting smaller. So that's the 1 over n plus 1 is less than 1 over n. We're good. We want to make sure that as you go out to infinity, that your nth term really is getting so small that it approaches 0. And we are also good with that. Okay, so double check, write out the statement first, make sure it makes sense, and then check mark if it does make sense. And then your conclusion for this is that this series is conditionally convergent. Okay, so what makes the problem now more complicated is you throw a variable in it. And when you throw a variable in it, now the question becomes find, instead of whether it converges or diverges, it's find the interval of convergence. So these are your 5, 6 point questions on the AP test on the series. Okay, it doesn't look too bad, but I know there's aspects of it where students might forget this one particular step, which I'll talk about, and I'll make you guys write in an exclamation mark. Actually, let's write that at the top so I don't forget to tell you guys. So you must do something called test endpoints, and I'll talk about what that means. And sometimes that's half the credit is testing the endpoints. Okay, so if we take a step back, we're just trying to find X values that make this series converge. Okay, that's all we're doing. We're trying to find X values that make this series converge. So the first step is you notice, well, what test do I use, Mrs. Kim? I notice that I have n in the exponent, I have n not in the exponent. So automatically ratio test. If it looks complicated, move to the ratio test. For the ratio test, you're gonna jump into the ratio test like you jumped into the top taking the absolute value. You're going to automatically always test for absolute convergence first. So if I take the absolute value of this expression, this -1 to the n plus 1 is going to drop. So I'm not going to even include that in my ratio test because I'm testing for absolute convergence. I want this to converge absolutely for certain values of x. Take the absolute value of it and then move on from there. So we're going to do limit as n approaches infinity. We're going to drop the alternating piece because we're taking the absolute value anyway. The only thing that could potentially be negative is your x values. So we're going to stick the absolute value this time around just the x. And remember, it was the n plus 1 term over the n term. But n plus 1 should be a quantity that we multiply by 2. So it's 2 times the quantity n plus 1. And then we put it all over 2 times n plus 1. Okay, this is your n plus 1 term, or the absolute value of your n plus 1 term. Then remember, it's supposed to be divided by the n term, but instead what we're going to do is multiply by the reciprocal of the n term. So that's going to be 2n over the absolute value of x to the 2n power. Okay, so at some point, as we do these problems, I'm not going to actually regroup things. I'm just going to actually maybe color code it for you guys. These two guys go together. And then these two guys go together. Okay, the x's are exponential, so you simplify them as exponential terms. So just keep in mind that when you guys have two quantity n plus 1, 2 times quantity n plus 1, that this is really 2n plus 2, right? And at the bottom of this is really 2n plus 2. Okay, so now using rules of exponents, what is left if you guys canceled out if you simplified the yellow highlighted portion, the x's, what do you guys have left for that? Okay, 2 as the exponent. If you subtract the 2n to the top, you have absolute value of x squared left over. The n's for the 2n and the 2n plus 2 is not in the exponent. It's a limit question as n goes out to infinity. So as n goes out to infinity of this expression, we take the ratio of the leading coefficients because the powers are the same, and we get 1 as the answer. So we get x squared over 1, or x squared is just your answer, right? What was the parameters at the beginning for ratio tests? That whatever answer you guys got must be less than 1. Okay, solving the absolute value of x squared is less than 1. To simplify that process, it's the same thing as absolute value of x must be less than 1. So I guess just to make it easy, you guys can kind of think of it as just taking the square root. It's still going to result in absolute value of x must be less than 1. Put that between as a compound inequality, x must be between -1 and 1 so that the distance is less than 1. That's what absolute value means. Okay, so here is where, and I didn't save enough room over on the right. Did I save enough room on the bottom? Okay, so this is half the credit. Okay, right now what this is saying is that if you picked any values between -1 and 1, so say 1/2, 1/3, 1/4, you plugged it in for x, that this is going to result in a series that is absolutely convergent. However, we don't know what's going on at 1 and at -1. So what we have to do is double check, is it convergent at x equals 1? Is it convergent at x equals -1? And this is the testing the endpoints part. Okay, so when you guys get down to these types of questions, which we're going to practice a ton next week, you're going to always remember this is only half credit right now. You guys have to test the endpoints. So what does it mean to test the endpoints? And this is where, if we were in class together, I know I'd get a lot of like, oh my gosh, like this is so long, and it is. Okay, so on the right-hand side, what I'm going to do is test each one of these endpoints. And what that means is you're going to generate a series with -1 as the x value. So what that means is if I took -1, which is this endpoint right here, plugged it in for x, there's going to be a series that results from it. And I have to test that series. Okay, so let's plug -1 in for x. And I'm going to do a literal plug-in first, and then point out something to you guys that is So subtle, but so important. And the answer to this, Kaylee, I'll answer that question in just a minute because there is going to be a type of question that you guys have already seen before, but I'm just going to remind you guys of it for the quiz. Okay, -1. This is the part that I want to make sure I take the time to explain carefully to you guys. Please make sure in the next step after you plug, and again, just what I did was I plugged -1 in for x. I replaced -1. If both these guys, if you have two expressions with the same base, please simplify that first by combining it. Don't just assume that you're just, it's not there, or just make sure you just simplify it first. Okay, so that means that if they both have the same base, you're going to combine the exponents by adding the exponents. So n equals 1 to infinity, keep the base, add the exponent. 2n plus 1 is 3n plus 1, all over 2n. This other step that I'm not going to show any work for because you guys are all going to remember to do this is double check. Now that you have a new exponent here, that's really not familiar to many of us. If you can double check, if I plug 1 in, then 2 in, then 3 in, does it result in a series that's alternating or not? So yes or no, you guys, go ahead and plug 1 in and then plug 2 in. Is the series still alternating? Because sometimes the answer is no, and sometimes it's yes. And that makes all the difference for what we do after that. Okay, so if I plug 1 in, I get 4, which is even, that's positive. If I plug 2 in, I get 7, which is odd. That's going to remain negative. So it results in positive, negative, positive, negative. So this is still an alternating series. So now the absolute convergence discussion, that's going to happen in your head now. Okay, so when you look at this, if you were to take the absolute value of this, does it converge or does it diverge? Oh, actually, one other thing I'm going to make note of for you guys up here. When you guys have the integral of 1 over 2x, is this equivalent to 1/2 over 1 over x? That's equivalent, right? We could pull the constant out. So this sigma notation or summation notation, it works the same way. So if you guys have any sort of constant tied to it, you can pull that constant out front. So, and then analyze the series as just 1 over n. So that's what happens here. If you pulled the 1/2 out, you took the absolute value of it, you pulled the 1/2 out, does the series converge or does it diverge? Okay, it results in your series of 1 over n to the first, which diverges. Notice that I don't have to write that out now. That's going to be a step that I analyze. Then I'm going to move on from there. It was alternating. So now what I'm going to do is apply AST. You have to show the AST part of it. Okay, in doing the AST, reminder, the first step was to show that your terms are getting smaller. So 1 over quantity 2n plus 1, your n plus 1 term, is indeed less than your nth term. Okay, write it out, then verify, is that true? If I add plus 1 to a denominator, it's going to make my denominator bigger, resulting in a smaller number for the n plus 1 term, so that checks off. Second part is write it out, then analyze. Let the limit go to, let n go to infinity of your nth term. Notice that I dropped the alternating piece to it, the negative part, we don't have to worry about that. Make sure that this is equal to 0. Write it out first, double check if it's true. It is true. This is going to, this analysis is resulting in the fact that this series is conditionally convergent. You only need conditional convergence in order to include an endpoint. So I'll just make a note here. Only need conditional convergence. To include endpoints. So what does it mean to include endpoints? So I'm going to draw this little bubble thing here and then draw an arrow, because sometimes I have kids, they do all of that work, but then they forget to go back. Include the endpoint means that -1 is going to result in a series that's conditionally convergent. So I'm going to include that endpoint. So that's going to be equals to -1. Guess what you guys have to do also? Test what else? And so this is why it's such a long problem, is that you have to test both endpoints. What's the next value you guys would plug in? Okay, and I ran out of the room. I normally test them side by side over on this side, but I'm gonna go ahead and just do it down here. So sorry for it being a little bit messy here, but this is me testing x equals 1. So go ahead and do that, and it should be easy after a while in testing the second endpoint, because you'll either notice that there's the same exact series that results, or it'll result in a simplification that you don't have to go any further. Okay, so here is the subtle difference, you guys. On the right hand, or sorry, on the first series that we did, this -1 had the same base, so I combined them to be -1 to the 3n plus 1. Over here, -1 and 1 is not the same base. Okay, so don't confuse it. Don't try to combine it at that point. I see that happening sometimes. -1 is not the same thing as +1. +1, kind of confusing as well, but if you have +1 and you're taking it to whatever power, what does that result in? 1 to the whatever power is equal to 1. So essentially this guy is not there anymore. And if he's not there, then is your series alternating? Okay, so it's alternating. Then the analysis after that, you have to show your work, but it's the same exact thing as the previous one. If you take the absolute value, it's going to be divergent by P series. So it's not absolutely convergent, but we're testing for conditional convergence by doing AST on it. Okay, your steps are the same exact step because the absolute value is going to yield the same exact series. You just have to write it out and verify that it's true, which we already know is true from the previous one. This is considered testing the endpoints. Okay, and since it does work out, because we already did it, to be true as well, we're going to include our endpoint. So this analysis is going to include the endpoint of 1 as well. So our final answer, actually all of that work, this is your answer. This is the interval of convergence with the equal signs at the bottom. And the work behind the equal signs is the testing of the endpoints that I'm going to keep saying, don't forget to test endpoints, you guys. And yes, these problems are very painful. There's so many steps involved in each one, and they get easier. I want to say you guys have to, I mean, there's a lot of work that goes behind getting to a point where you're comfortable with this, but we will work Wednesday on the same type of thing next week. Oh, yes. Yeah, so Min was saying this is kind of like one of those questions on the AP Bio test where it's like A through F. And yes, it is like one of those questions. I have 5 minutes left and I want to make sure I cover this question because you guys can answer it already, but I want to make sure that it makes sense to you guys for the quiz. So if you guys can go back to page 31. Kaylee asks, will this be on the quiz? This is not going to be on the quiz, but I want to make sure you guys see the link and the ability to recognize it in both ways, like solving it in both ways. So you do have a question like number 12 on the quiz. Okay, if we did not cover ratio tests, I would still expect you guys to be able to answer example number 12 with information from what you guys already know. So what type of series is number 12 in the chat? Not ratio test, but what type of series is that? And Tim, the question we just did, we did test endpoints. The beginning, it was alternating. So yes, you do that if it's alternating. And testing endpoints only involves when you're solving for X. Okay, you guys, if I can tell you guys to look back at your notes at some of the power series stuff at the beginning when we were doing this, because we did a question like this at the very beginning. Now you guys have 2 ways of attacking this problem. There's been years where there's a free response, and the free response has basically 2 options for an answer. One option is like 2 steps. The other option is 10 steps. Okay, so here's the 2-step part of doing this question. We recognize it's a geometric series. How do I know it's a geometric series? we see that it's a common ratio to the nth power. So if you have something raised to the nth power, it's automatically geometric series. If you don't believe me, plug 0 in and you guys get 1. Plug 1 in, you guys get x plus 5. Plug 2 in, you guys get x plus 5 squared. So we're multiplying by x plus 5 to get from one term to the next. So if I recognize this as a geometric series, I know the condition for the interval of convergence for a geometric series is that the absolute value of the common ratio must be less than 1. Or many of you guys before just put it between -1 and 1, right? And then we solve for x, subtract 5 on both sides, we get x is less than -4. And another common mistake, don't do this on the quiz, is to think the other side is going to be like +4 or the same value, but just opposite in sign. Make sure you actually subtract 5 on both sides to get -6. And you're done. For a geometric series, you don't have to worry about endpoints. It will not be convergent at the endpoints. Okay, it won't be convergent at the endpoints. It's not alternating. So this is your final answer. Okay, this is on a free response, and I swear this happened. It says, recognize it was geometric. This is the answer. If you don't recognize this geometric, then you apply the ratio test for it. And if you apply the ratio test for it, it will say in the work, did they test for endpoints? So if, again, we could also do this by geometric or by ratio test. So this is recognizing it's geometric, and you're done. If you don't recognize it's geometric, and you guys then apply ratio test to it, it's absolute value of x to the n plus 1 over absolute value of x plus 5 to the nth, which is then just absolute value of x plus 5, and that is less than 1. Notice that you guys get the same exact results here, but when you show this step, then they're like, oh, okay, this person didn't recognize it was geometric. They're doing the ratio test. So if they did the ratio test, they have to show that they tested endpoints. So after you guys solve for this, then they would have expected on the free response for that year that you plug -6 in, that you plug -4 in to x and test the endpoints from there. So I'll just make a note because I don't want to really do it, but you must test endpoints after that. Okay, so I'm not doing it also because it's a point of emphasis I want to make. You guys want to save the time, and if it's geometric, automatically do the method on the left. I guess if it's worst comes to worst, anytime you guys are applying the ratio test and you're solving for x, you have to test endpoints. That is not the only example we're going to go over. We're going to go over a ton more on Wednesday, but they're basically like the same type of things. It's just at the very end, you might get a series that is a little bit different from the P series or geometric, and then talking about what to do from there. We're almost through with the series chapter, you guys. I would say we have about like a 5% of material left. This is the bulk of it. This ratio test, this interval of convergence, that's the big part. So if it didn't make complete sense to you guys, I think don't worry about it too much. Don't worry about the testing of endpoints for the quiz. It's going to be mainly on Taylor series still. Lagrange error bound is going to be on there. I listed the topics that are going to be on there on your at the bottom of the agenda. Also, if you guys can double check your first quiz, make sure that the mistakes that you made, that it makes sense to you guys. And if you are worried about the quiz, you can hop on at 4:30 today. I'll be on Zoom at 4:30 if you guys have any additional questions and you can make it. I'll see you guys at that time.